Hi there matriculants and welcome back to NTE. In this video what we're going to do is we're going to give ourselves a chance to practice some electrochemistry. Right. We're focusing on today is November 2014, right, and we are looking at question number 8 and question number 9. Right. So let's get started. Okay, so in question number 8, right, we have a standard electrochemical cell, right, which has been set up over here. Okay, part of it is the She cell, okay, so the standard hydrogen cell, okay, and the other part, right, is made up of an unknown component, right, but all we know is that in the solution, okay, we've got the positive cations of that component, okay. A voltmeter is connected across the cell, and initially the reading, right, on this voltmeter is 0.31 volts. Right. So if we just quickly look at the elements of the cell, we can see that what we're seeing over here is a voltmeter. So this automatically qualifies this cell, if you didn't know, as a galvanic cell. If there was a battery over there, then it would have been a electrolytic cell. Right, remember that we also call galvanic cells voltaic cells, right? That means exactly the same thing. Okay, so now you also need to know that if this reading, right, on the voltmeter is positive, it indicates that the flow, right, of electrons in this external circuit, right, is from right to left. Okay, so this is the direction of electron flow. Okay, so now that we know that electrons are flowing in this direction, we can identify that what's happening here in this part of the cell is going to be oxidation. Okay, which is automatically going to mean that we need to have reduction happening on the other side, right? Because remember, those two processes can't happen individually. Okay, so how did we come to the conclusion that oxidation must happen on this side? By simply looking at the reading on the voltmeter. Okay, so the reading on the voltmeter was positive, which indicated to us that the direction of electron flow in this external circuit, so basically we're talking about the direction of electron flow in this wire over here, right, that was in the direction of right to left. Okay, so which means that those electrons were supposed to be coming from this half cell, okay, and oxidation is the one that releases electrons, so the process of oxidation is occurring in this half cell over here, right. So now we can write down a little bit of the skeleton, right, half reaction for what's happening here on the right hand side, okay, this right hand side beaker. Because we've already identified that we have oxidation, we can write that oxidation half reaction okay, as basically, right, X, okay, whatever this X is, it's going to give away 2 electrons and it's going to become X2 plus in solution. Okay, so now if we just quickly identify our components as well, right, this electrode, right, you can see there's a negative sign next to it, and it's also a galvanic cell, so that is our anode. Okay, so this is our anode, and I'm just going to shade it in blue, right. So now that we've identified our anode, we can now confidently say that on the other side, okay, this platinum over here, right, this little piece of platinum over there, right, that is acting as our cathode, right, and I'm just going to write it next to this positive sign over here, right, that is our cathode. Okay, so that's referring to the small, you don't really need that much, okay, this small little piece of platinum. Right, Let's just write in the voltmeter reading as well over here so we have it for reference. Okay, so there we go. Got electrons flowing in this direction. Okay. And then now let's quickly just jot down the reduction half reaction. Okay, that's supposed to be happening on this other side. I'll just move this to here. Okay, so the reduction half reaction. Okay. You can get this from our table 4a, right, which is showing us the standard reduction potentials, right, or you can just understand what is happening over here. Okay, so basically hydrogen gas is coming in through this tube, right, and it is being bubbled into a hydrochloric acid, right, solution. So you've got H plus and Cl minus in solution over here. Okay, so then basically, if your hydrogen half cell is actually undergoing reduction, then you know that these species inside of the solution, right, so your H plus, they are the ones that are actually gaining electrons. We just put an electron for now, right, and then they become hydrogen gas, right, so they bubble out. Those bubbles that you're seeing there, that is hydrogen gas coming out. Okay, so now let's just balance this quickly. Remember that from the oxidation half reaction, we determined that 2 electrons were being given out, right? Okay, so then you have to balance this half reaction by putting a coefficient of 2 here for the H plus and a coefficient of 2 there for the electrons, and we already have the hydrogen gas nicely balanced for us. Okay, so let's just quickly go to the standard reduction potential table just for me to show you this reaction. Okay. Okay, so here is our standard reduction potential table, right? You'll find this at the back of your paper, right? And like I said in the beginning, this is specifically table 4a, right? In these videos, I'm always going to be referencing table 4a, right? So that's the one where your standard reduction potentials are listed in decreasing order. Okay. So if you scroll down this table, there you'll see that reference cell that we were looking at. It's right over here with a standard reduction potential of 0 volts. Okay, and because this is a standard reduction potential table, right, this equation as written, okay, is basically describing a reduction half reaction. Okay, and that's exactly what we wrote down. Okay, so you could have just taken it from the table directly. Okay. Right, so now let's move on to the questions, right? So 8.1 simply says, besides concentration, right, write down 2 conditions needed for the hydrogen half cell, right, to function under standard conditions, right? And the key term over here is standard conditions, okay? So now remember that the hydrogen half cell is this half cell over here, okay? So this part, just this part, okay, that is the hydrogen half cell, right, and it's composed of something in solution, right? We've got hydrochloric acid in solution over here. So basically we already have on the screen that the concentration of that solution has to be 1 mole per decimeter cubed, right? But then they want us to say something else other than the concentration of the solution, right? And that's just basically going to be that this experiment, right, has to be conducted under room temperature, which is 25 degrees Celsius, and it also has to be conducted under a pressure of 1 atmosphere, right? So this gas, right, this hydrogen gas has to be under a pressure of 1 atmosphere. Okay. Okay, 8.2, right? It says, give 2 reasons, besides being a solid, why platinum is suitable to be used as an electrode in the above cell. Okay, so the fact that platinum is a solid, it basically gives sort of like an area, right, for the electrons to move in, right? So remember that metals are good conductors of electricity, right? So it gives those electrons a place, right, to actually travel in. Okay. Another reason that we use platinum, okay, did they say 1 or 2 reasons? Let's just check. Okay, 2 reasons, right? So then we have to write down that first statement as well. Okay, so that's 1 reason. A second reason is because platinum is an inert metal, right? So it doesn't take part in this reaction. Okay, and we can also confirm that by looking at our table 4a, right? So there's the hydrogen. Okay, if we just look at where platinum is on this table, right, you'll find it right over here. Okay, so then relative to hydrogen, okay, it's much higher up this table. Okay, so if you watched the previous video, you would have seen that I use something called direction arrows, right, to help you to decide between what is a better oxidizing agent and what is a better reducing agent. Okay. Okay, so if you compare the reduction half reaction of hydrogen and that of platinum, okay, then you will see that platinum 2 plus ions, right, those are a stronger, because it's higher up on this table, right, these are stronger oxidizing agents, right, whereas the platinum would be a weaker reducing agent. Okay, so now in our experiment we are not using platinum 2 plus ions, right? This is not what we have. What we have is just solid platinum metal. Okay, so solid platinum metal is a weaker reducing agent, so it's not going to actually take part in this reaction. Okay, so in other words, it's not going to undergo oxidation, right? So whatever else we pair this cell with, okay, that's going to undergo oxidation so long as it's anything below platinum. Okay, because any species below platinum over here is a much stronger reducing agent compared to platinum. Okay. Okay, question 8.3. It says write down 8.3.1 the name of component Q. Right, let's just go back to the sketch and see. Oh, okay. Component Q is this component right over there, so that is called a salt bridge. Question 8.3.2, right, says write down the standard reduction potential of this unknown half cell. Okay, so if we just go back up, right, we already identified that this unknown half cell is undergoing oxidation, right? So it is basically the standard reduction potential of our anode, okay? And we are given the standard cell potential as 0.31 volts, okay? And we already know that the standard reduction potential of a hydrogen half cell is 0 volts, okay? So we can just quickly calculate what is the standard reduction potential of our unknown half cell. Okay, the standard reduction potential at the anode, okay, that's going to be equals to, well, if you subtract 0 on both sides, you still have 0.31 volts. Then you need to divide that by a negative, so this is negative 0.31 volts, which also confirms why that unknown half cell is undergoing oxidation, right? Because its standard reduction potential is negative, which means that it prefers, right, to be oxidized rather than to be reduced. Okay. Question 8.3.3 says write down the half reaction that takes place at the cathode of this cell. Well, we already wrote that down. Okay, right in the beginning of this video. The answer to that is 2 H plus ions gaining 2 electrons to form hydrogen gas. Okay, so this is basically 8.3.3. Okay. 8.4, right? The hydrogen half cell is now replaced by another unknown half cell, which they're calling M. Okay. The cell notation for the cell is given as follows. Okay, so remember that cell notation is something that we only write for galvanic cells. Okay, and the components of your cell notation is always a matter of this first part before the salt bridge, right? Because remember that double line is the salt bridge. Okay, it's always in a way that what comes before is talking about what's happening at the anode, okay, and then what comes after is talking about what's happening at the cathode. Okay, then again we're now told that when they set that up, okay, the voltmeter is reading 2.5 volts, okay, which again tells us that the direction, okay, of electron flow is from the right to the left. Okay, so basically if we can try to imagine this, we know that we're going to have a salt bridge. Okay, and this salt bridge is going to be dipped inside of two separate half cells. Okay. Right, and in these half cells we need some sort of electrodes. Okay, so now because we already saw, because of this value over here being positive, that the flow, right, this is the direction of electron flow. Okay, if the voltmeter reading is positive, means that our electrons are flowing from right to left. Okay, so which means that we have oxidation happening on this side, and oxidation always occurs at the anode, right? And we already identified the anode piece to be this part with the M, so that means that this metal is called metal number M, right? Whatever that is. And in solution over here, right, let's just put some color in this. Let's just say it's the sky blue solution. It's not to say that this is true in reality. Okay, and on the other side we'll have some green solution. Okay, all that we are really saying is that this solution in here, right, is going to be some solution that contains M2 plus ions, right, and the one on the other side, okay, is going to have to be our cathode. And what happens at the cathode? Reduction. Okay, so from what we are given from the cell notation is a metal X, right? And inside over here is some solution that contains X2 plus ions, right? And what's going to happen over here is that as these electrons are coming into this cathode half cell, right, these X2 plus ions are going to be attracted to the cathode and be reduced. Okay, and then on the other side, the M, right, metal is going to be oxidized and it's going to go into solution as M2 plus ions. Okay. So now obviously they're going to want us to identify this M and X. Okay. Right, so if we just quickly calculate that, right, this is 8.4.1, back to that equation, E naught cell, okay, is equals to E naught cathode minus E naught anode. Okay, I'm just going to make this a little bit more specific to our situation. Okay, we're going to have that the E naught of this cell, okay, is given by the standard reduction potential, right, which is happening at the cathode, right, and our cathode was basically that species X, right, so this is the reduction of X2 plus going to X, right, and we need to subtract from this the standard reduction potential, right, of the reaction that's occurring at the anode, right, and that's going to be the M2 plus going to M, right. Okay, so this is what we want to calculate, the standard reduction potential of M2 plus to M. Okay, so let's just jot in what we know. We know that the standard cell potential was given to us as 2.05 volts, and we calculated the standard reduction potential of X2 plus to X as minus 0.31 volts. Okay, and now we are able to solve for this. Okay, so then therefore the standard reduction potential of M2 plus to M is going to be, okay, so that works out to negative 2.36 volts. Right. So negative 2.36 volts. Do a sort of like comprehension check, right? Does it make sense that if the standard reduction potential, right, of a species is negative, that species has to be at the anode? Yes, it does make sense, because then it means that that species, whatever it is, right, it doesn't want to be reduced. It would rather undergo oxidation. Okay, and oxidation occurs where? At the anode. Okay, so let's go to our table and identify what is metal M, because that's what we're actually asked to do. Okay, right, so starting from the hydrogen half cell, okay, that's where we're going to start seeing the negative standard reduction potentials, and what we're looking for is going to be quite low down. We're looking for negative 2.36, so there it is. Okay, negative 2.36, that gives us that metal M is magnesium. Okay, so our anode is a magnesium anode, right? And it becomes oxidized, and then you get magnesium 2 plus ions in solution. Okay, read over here and say, therefore, metal M is magnesium. Right. Question 8.4.2, right, is asking, is the cell reaction exothermic or endothermic? Right, guys, this is just application of theory. You should have known, right, or you should find somewhere in your notes, right, that a galvanic cell is always an exothermic reaction. Okay, so the answer to this, I'm not even going to write it down, I'll just circle it over here. It's exothermic, right? And if you want a reason for it, this is just application of theory. Because this is a galvanic cell, the cell reaction is exothermic. Okay, so next. Question 8.5, the reading on the voltmeter becomes 0. Okay, so we currently have a reading here of 2.05 volts. They are saying it now becomes 0. Okay, so important thing to know over here is whenever you are looking at a galvanic cell, remember that a galvanic cell is basically just a battery. Okay, so whenever that voltmeter reading becomes 0, right, it means that your battery has gone flat. Okay. Let's just carry on reading. After using the cell for several hours, give a reason for this reading by referencing to the cell reaction. Okay, so the reason for this reason is because the cell reaction, what we're basically saying by saying the cell reaction is we're talking about these oxidation reduction reactions that are occurring over here, right? Those have actually now reached equilibrium. Okay, so that's basically going back to what we learned in chemical equilibrium, right? So the cell reactions, don't make the mistake of saying they've stopped. They haven't stopped. They've just reached equilibrium, right? So the cell reactions have reached equilibrium. Thus, the voltmeter reading is 0. Okay, and it's as simple as that. Now moving on to question 9 from this paper. Okay, we have over here that what's drawn is simplified diagrams that represent two electrochemical cells, A and B. Okay, so in both of these cells we have concentrated copper 2 chloride. Okay, so let's first start off with electrochemical cell A, right? So first things first, what we see over here is that we see a battery. Okay, so because we see a battery, it means that this is a electrolytic cell. Same thing for electrochemical cell B, we also see a battery, so this is also a electrolytic cell. Okay, notice where the positive terminal is, right? This means that this is our positive electrode, but in this case, because this is an electrolytic cell, the positive electrode is called the anode. Okay, and then this is the negative electrode, and it's the cathode. Right? Okay, so now let's talk about electron flow in the external circuit, right? And I'm going to highlight the external circuit again. It's this wire over here. Okay. Right, so just a quick note, don't confuse the electron flow in electrochemistry, right, with the electron flow that we see in electric circuits, right? So remember that in electric circuits, we're looking at conventional current, which means that electrons flow from the positive terminal, okay? They come out of the positive terminal, okay? But now, over here, what we're doing is we're just looking at the proper nature of electrons, right, which is basically them flowing from the anode to the cathode. Okay, so which means that our electron flow over here is in this direction. Okay, I can even just put that in over here in cell B. Okay, that's the direction of electron flow. Right, so in cell B, what we see in contrast, right, is two copper electrodes, right? So which means that this is going to still be a process of electrolysis, right? And what is this going to be? It's going to be most likely the purification of copper, right? So one of these copper electrodes is going to be the impure, right, copper electrode. Okay, but it still stands that this electrode R is positive and is the anode, and the electrode T is negative and is the cathode. Okay, so let's jump into the questions and see what they want us to answer. Okay, question 9.1 says, are cell A and B electrolytic or galvanic cells? Well, we already answered that question, and the thing that made us to answer it was this presence of batteries in both of these cells. Okay, so I'm not going to even write this down, I'm just going to circle it again. Okay, both these cells are electrolytic cells. Okay, remember that when you see a battery, it's electrolytic. When you see a voltmeter, it's galvanic. Okay. Question 9.2 says, which electrodes P, Q, R, or T will show an increase in mass, right? Write down a half reaction to motivate your answer. We identified cell B as being the purification of copper. Okay, so this is the purification of copper. Okay, so which means that one of these electrodes is going to increase in mass, right? And it's going to increase in mass as the impure electrode basically gets oxidized. Okay, right, so which one is going to be which? Well, we know that the impure electrode, like I just said, it needs to undergo oxidation, right? So where does oxidation occur? Oxidation always occurs at the anode. Okay, so this is where oxidation occurs, right? So which means that electrode R is impure copper. Right, so there's other substances in this electrode, which means that we're going to have that sludge that gets formed at the bottom of electrode R, and this is also valuable because they can get other precious metals out of this. Okay, so now to answer the question, which one of these electrodes from the list is going to increase in mass? Electrode T. Okay, so the answer here is T. That's the electrode that's going to show an increase in mass. They want us to write down the half reaction to motivate our answer. Well, electrode T is at the cathode, and what happens at the cathode is reduction. Okay, so basically what's going to happen is this is solid copper, right? So the solid copper is going to be oxidized and some of it will go into solution, right? So like I was saying, okay, the copper 2 plus ions in solution, okay, will then be attracted to the negative cathode, right, and they are going to be reduced, right? So then the half reaction that we are writing over here is a reduction. Half reaction, I'll just write RXN, okay, and that is the copper 2 plus ions, right, basically gaining. I'll just write an electron for now, I'll balance it after. Okay, they're basically going to be gaining electrons and then become solid copper. Okay, so if this is a copper 2 plus ion, it needs to gain 2 electrons in order to become solid neutral copper. Okay, but now when we actually look at cell A, right, we notice that at the cathode, the same reduction half reaction of copper 2 plus ions, right, gaining 2 electrons to form solid copper, will also happen at electrode Q, right? So electrode Q is also going to increase in mass. Okay, so let's just quickly talk about what's going to happen here at cell A. Remember, this is the decomposition of the copper to chloride solution. Okay, so what's happened over here, right, is that you have a concentrated solution of copper to chloride, right, and the Cl minus ions, right, will obviously be attracted to this positive anion, right, so they're going to sort of like build up next to it like this, and then they are going to be oxidized and they're going to give up, right, for actually, okay, so for every 2 mole of chloride ions, right, so when I say 2 mole I mean like that, okay, so for every 2 like that, right, they each give up 1 electron, okay, and those electrons go when they flow in the external circuits, and they go and they go and they go, and they build up here on the cathode, right, so they basically build up over here, okay, and then you can see where this is going, right, okay, will basically just be attracted to these electrons, and then they're going to be reduced, okay, with the same formula actually. Okay, right. Okay, just to make this a little bit more complete, okay, what happens after 2 moles of chloride ions actually become oxidized here at the anode? Well, they combine and they become neutral, right? What's going to come out over here is chlorine gas. Okay, right, so we say that they bubble out of solution. Okay. Question 9.3, right, it says write down the name or the formula, right, so don't write down both, the name or the formula, okay, of the product formed at electrode P and electrode R. Okay, so let's go back. Okay, so for electrode P, I already told you that what's coming out over here, right, is chlorine gas due to the oxidation of 2 moles of Cl minus ions. Okay, so for electrode P, okay, what's better? I think the best thing to do is to use the formulas. Okay, what's being produced there is Cl2 gas. Okay, let's go to electrode R. Electrode R is here in cell B, right? Purification of copper. Okay, so the product that is forming at electrode R, as indicated with this arrow, right, is this copper 2 plus ion going into solution. Okay. Question 9.4 then says, fully explain the answer that you gave in question 9.3.2 by referring to the relative strengths of the reducing agents involved. Okay, so if we go back to question 9.3.2, right, we were looking at the product that formed at electrode R, and we said that that product is copper 2 plus ions. Okay, so now they want us to explain why the product that is formed at electrode R is actually copper 2 plus ions. Okay, alright, so for this we are going to have to go to table 4a, right, so that I can explain to you why is it that copper 2 plus ions are going into solution. Okay, okay, so now back on table 4a, right, remember the direction arrows, right, which basically help us to determine the relative strength of our oxidizing agent and our reducing agent. Let's first find the two half reactions that we are being asked to compare, right? So the first one is right over here, the one that contains Cl minus ions. And the other one is copper 2 plus right here at the bottom with the solid copper for our anodes. Sorry, for our electrodes. Okay, if we take our direction arrows, okay, we put it on this table, right, you'll be able to see that for what the direction arrow is pointing to, okay, to the left and up, right, which is going to lead us to this chlorine gas, okay. Chlorine gas is therefore going to be a strong oxidizing agent. Okay, that's according to the direction arrow. Or you can just remember what's written on the side over here. Okay, as you go upwards on the table, you see increasing oxidizing ability, or that basically just means that you have a stronger oxidizing agent. Okay, now on the flip side, the direction arrow is telling us that our strong reducing agent has to be this one right over here, which is copper. Okay, so copper is a strong reducing agent. Okay, so what are we dealing with in our situation? Well, we're dealing with the copper, right, as the electrodes, and then there is Cl minus ions in solution. Okay, this is not really involved in the reaction. What we are looking at is Cl minus ions in solution. Okay, so now they, in comparison to the copper, will be weak reducing agents. Okay, so to put it in words, what you want to say over here, right, is that remember that we had to comment on the relative strength of the reducing agents. Okay, so from what we just saw, copper, right, so solid copper is a stronger reducing agent compared to the Cl minus ions, right, so Cl minus ions. Okay, therefore, right, you know most, the strong always win, right, so then therefore, instead of the Cl minus ions undergoing oxidation, the copper undergoes oxidation at electrode R, okay, to give Cl2 plus ions as a product. If you want to, you can even give the half reaction. Right, so that's it for today's video, matriculants. I hope you guys learned something, and I will see you next time.